welcome. I hope everybody is ready for this session. I am Ahmet Ursul Alkan, the Congress Chair and also Professor of Yıldız Technical University. We are all, with the colleagues, we are here at the Yıldız Technical University Hydrodynamics Research Laboratory. There are also a screen, you see the general view of the laboratory. May I introduce briefly, very briefly, because we want to listen all you first, but we give a very, very brief information about the wave basin. I should share this screen. Yeah, it is difficult in these times. Where is it? It is here. Yeah, YTU Hydrodynamic Research Laboratory, HRL. It is located in Davutpaşa, Esenler district of Istanbul, the Davutpaşa campus of Yıldız Technical University. The area, not size, but the area is about 5,000 square meter, integrated with hydraulic and coastal laboratory of the civil engineering department, civil engineering faculty. There are two divisions in this large laboratory. This division is Hydrodynamic Research Laboratory for ship and coastal structures. There is a good capability here. The dimension of the wave basin in gross dimensions, 28.85 width, and the length is 36.43 meters. The water depth is 220 centimeters. There is a wave maker system. I should say in Turkish maybe it is dalga yapıcıyı gösterdiniz değerli hocalarım. Dalga yapıcı. Wave maker, there is a HR Wallingford built multi-directional wave generator. This generator has 48 pedals. 48 pedals. Capabilities, what about the capabilities? I am finishing now. The wave generator has regular and irregular wave generation capability with different wave spectrums. Short and long crested directional waves will also be generated. The wave generator is a snake type wave generator. I hope within seconds we will see some movement on this model without instrument. There is a container model floating. I can, in a few seconds, I will pass to the presentations. Your valuable presentations are very important for us to know each other, also to make contribution to the conference, to the symposium. I am very sorry, to the Congress. But before it, let's calculate the time and the talk order. After Claudia Pensa and Fabio De Luca, I think Levent Kaydıhan has a meeting. He needs 5 or 7 minutes. Then we continue with the order written in the program, please. I give this information. I say something to my colleagues. Çalışma arkadaşlarımız buradalar diyeceğim. Ne zaman göstereceksiniz Hasan Bey? yeah, in a half minute, we will turn to the presentation session. Thank you very much. Now, there are the faculty, the Naval Architecture and Maritime Faculty Dean, Professor Yilmaz, and Head of Department, Professor Ekinci, and other research assistants and assistant professors. I can say names: Ali, Ömer, Onur, Süleyman, and students also here. We just greet you, and I think it's better to start with the presentations. Italian colleagues, Claudia is here. Yeah, Claudia and Fabio De Luca. The floor is yours.
Okay,
please.
Thank you very much. Good afternoon to all of you, wherever you are. First, in addition to Professor Alcan, I would like to
slide we can't see the slide.
You don't see me?
Yeah, I stopped sharing.
Okay.
Mr. Saushudai, welcome. Sorry.
Nothing. I say that I want, in addition to Professor Alcan, I would like to thank the organizing committee and the Indies Technical University for kind invitation. With this brief speech, just a moment, just a moment.
Yeah, of course there are.
Tell me when you see my screen.
No, it's okay.
Okay. So I say that I would like to present some of our research activities, both studies in progress and projects still in planning at the Laboratorio Hydrodynamic Experience of Naples in Italian Lane. The main features of the towing tank are shown here. As you can see, it is a medium-sized basin, but with a large cross-section that allow us to test models of a considerable size, particularly of a considerable width. The most demanding activity performed in recent years is the characterization of the Naples warped hard-chine systematic series. This is composed of 5 models of different aspect ratio designed for the volumetric fluid number range 4.82 to 7.82, or if you prefer, fluid number 0.5, 1.6. So far, still water test with and without interceptor, and tests in waves without interceptor have been completed. Tests in wave with interceptor are in progress. Self-propulsion tests are planned for 2022. Other ongoing research includes the study of lubricant impregnated surface, LIS, and the air-lubricated hulls. To perform the test on the LIS, a colleague from the measurement lab designed and built the weight mechanism you see. The principle of operation, already applied by other laboratories, has been adapted to reach Reynolds number higher than those realized to date. Essentially, the equipment was designed to test longer plates at higher speeds, achieving Reynolds number magnitude greater than 10 to the power of 7. The experimentation in progress evaluates the performances of the different solutions in relative form, comparing the resistance in relation to a sample plate. The dimensions of the plate, 3.0 for 0.8 meters, and the maximum speed reached 5.5 meters per second, amplify the main criticality of the tests, i.e. the resistance generated by the lift due to the errors in alignment of the plate with respect to the direction of motion. To minimize these parasitic forces, a meter for the rotation of the plate caused by the lift was applied. Based on the measured rotation, the aft constraint of the plate can be moved to correct the alignment. These translations are measured with a micrometer to identify the best position and make the obtained measurement highly repeatable. In this slide, you see the constraint here and here that were made in form of double pendulums, the rotation axis, and the load cell here and here, and I don't know if you see, and here. The application of two counterweights has also been envisaged. This aims to move the center of gravity of the mobile part closer to the rotation axis. By doing so, the restoring moment generated by the force of gravity is reduced. The alignment error is amplified, and the accuracy of the correction improves. With this system, we believe we can test longer plates at higher speed, avoiding the amplification of errors due to the greater weight. Here you can see also C micrometer, of which I said you, is here. This is the movement of the aft constraint. The study of high lubricated hulls will address planing, semi-planing, and displacement hulls. Referring to the latter, the diagram illustrates a typical application achieved by Mitsubishi. The tests on displacement hulls are scheduled for 2022. Now, tests on planing hulls are in progress. In particular, we are studying the blowing of air coupled with a double interceptor system, the DIS. The DIS is a high-lift device extensively studied by us in recent years. Its operation is based on the generation of two high-pressure zones, amplifying the lift, and one dry zone, reducing the wet surface. Here, in the lower left, you can see the forward interceptor is here, the dry zone, and the aft wet zone. This is the spray range, the second spray range, going west aft. The formation of the dry zone observed during the test have been filmed, and this is an example. In real speed, this one, and in slow motion. This has proved to be extraordinarily effective in reducing resistance, up to 25%. However, a few critical issues due to the ventilation difficulties of the dry cavity occur. In particular, the greatest difficulties were encountered with the warped hull, characterized by high dead rise value in the bow area, where the forward interceptor must be applied. Now I try to show the critical moment. You see that in this moment, the ventilation becomes effective, avoiding the low pressure due to the attachment of the fluid vane. For this reason, we believe that the coupling of the air blower with this can be an effective solution, especially to widen the speed range in which this is effective. Tests on models of different slenderness ratio, length over beam or length over displacement, are planned for the next few months. If the results are encouraging, we will start the systematic evaluation of this solution applied to the Naples systematic series. Although the lane is substantially illustrated for naval activities, the experience acquired by the team in tank experiments has led to collaboration with other researchers of our department. The image you see refers to research aimed at the production of electricity from the sea, both from waves and from marine and river current. On this slide, you see wave energy converter, WEC, tested first in small scale and then in two-side. The diagram shows the mechanism, the piston, actuator, and the load cell. And this is the WEC in action. We have tested also the mechanism with the wave, higher wave. As for the WEC, also the river turbine tests were here shown have been quite challenging due to the large dimensions to achieve high Reynolds number, which produced very demanding stress forces on the structure. Here you see GEMSAR, a floating underwater turbine test in two sides. On the right, you see the anchoring scheme to the dynamometric carriage we made in tank. The measurement lab also developed data acquisition and analysis software specifically to interact with the custom-made instrumentation and to facilitate the experimental procedure we developed. As an example, Professor De Luca will now show the software created to analyze the large amount of data collected with the Renewable systematic series. Fabio, tocca a te.
Good morning.
Grazie Claudio Pensa. Grazie.
Interrompo la condivisione.
Grazie.
Come no? Prego, prego.
Okay, I share my screen. Okay.
Okay.
I start my presentation. Just a moment. Okay. You can see my presentation?
In the presentation,
Yes,
presentator mode.
Okay. Good afternoon to all of you present here today. As Claudio said, 3 experimental campaigns have been carried out on the Naples systematic series. The first concerned resistance tests in regular, the second test in irregular head C, and the third in irregular head C. Results on the 3 activities are published in the paper here shown. In this presentation, we want to show the main criticalities concerning the experiments in irregular C on Naples systematic series. To make the great amount of data of a systematic series comparable, we perform more than 1,000 tests. The first step was to determine C states as accurately as possible. For this reason, capacitive probes were placed in several points of the tank, and an ad hoc transfer function were created for each of the 3 C states tested that were checked periodically during the experiment. A critical aspect due to the speed of the model and the length of the tank is the acquisition time. It's in fact necessary to carry out more than 1 test to reach an adequate number of encounters for the analysis of a single C state. Specifically, we perform 15 runs for each C state. For this purpose, a software was created in LabVIEW to combine the runs of a single C state. The first tool of the software allows you to choose the data acquisition window and simultaneously look at the measured C spectrum. This allows to improve the correspondence with the desired spectrum also in post-processing. Here. Okay, here. In this slide, we see the main quantities measured in a single run. Only 3 of the 12 are shown in the graph for a greater clarity. The upper graph has 2 sliders that can be dragged to change the useful capture window, shown in the lower graph. On the right, the measured spectrum and the expected spectrum of the C state are always visible, concerning the sum of the whole runs that compose a single C state. The queuing of data in time domain can be critical because it is necessary to identify a point that has at least a first derivative comparable. Here we see an example of bad alignment above and a good alignment below. In order to have an evaluation that is as clean as possible of the power spectra are estimated through Welch method that strongly reduce noise. This method involves the decomposition of signal into several sections and the use of Hamming windows, breaking the signal into groups with the same number of samples with an overlap of 60%. In this way, it is possible to have a very clean spectra by applying the same parameters to all the measurements. It is possible to reach an excellent level of comparability of the data. It is possible now to use another module that allows to analyze the different test conditions simultaneously. Here we see the initial screen of the software that allows you to select the seared files. In this case, we see 12 different conditions for the C1 hull of the Renewable systematic series with and without interceptor. Here are shown the signals acquired in time domain for one of the test conditions: 2 triaxial accelerometer, data from the Qualys motion tracking system, and wave measurement in 3 different points. Then data is processed by applying a bandpass filter from 0.1 to 12 Hz, identifying peaks, valleys, and heights, which are grouped into different data arrays. Therefore, you can choose one of these arrays and organize them by fraction of highest samples. Here we see an example of Eve analyzed for all conditions simultaneously, so it is very easy to compare data. In addition to the classical statistical analysis, an algorithm for fitting of the probability density function has been implemented. The algorithm allows you to fit the parameters of the statistical function on experimental distribution through Levenberg-Marquardt method. It is possible to choose a distribution from those implemented, like normal, Cartwright, logarithmic, extreme, gamma, Rayleigh, to obtain the parameters of the function for the whole condition simultaneously under the seared magnitude. The graph in red shows the statistic on experimental data. In blue, those coming from the results of parametric optimization. On the left is shown the probability distribution for a chosen condition. The graph in the center shows the significant value of the acceleration calculated by statistical function, the blue square, and the one processed on experimental data, the red square. Another tools allow you to apply normative analysis on acceleration, but I don't want to be too long, so I save the last interesting part of the presentation. So
thank you very much.
Yeah. I thank you, and I thank you. If there are any questions.
Yeah, I remember very well the colleagues in University of Naples, Federico Due, they are concerned with the high-speed vessels a lot. So still there are interesting and experimental studies. Thank you for your interesting presentation to Claudio Pensa, to Fabio De Luca. I think Levent Kaydıhan, yeah, will very brief.
Hello.
I think in 5 minutes you summarize.
Okay, well, it can take
please.
a little bit longer, but I will try to reduce it to 5 minutes. But okay, first I should share the screen. While sharing the screen, I would like to briefly introduce myself. Yeah. My name is Levent Kaydıhan from Marint, from Netherlands, and I graduated in Yıldız Technical University in '98, and after then I continued my master's degree and PhD also in Yıldız Technical University, and my PhD is about the structural vibrations, hydrostructural vibrations of the ship structures, and including the hydroelastic effects. And then I started work in the ship design office in Turkey, in Istanbul, and after 20 years having a wide experience there, I moved to Netherlands. Now I'm working in Marin in Netherlands for 3 years, actually. So I will just give a very brief introduction, Marin, because you may already know that kind of details. Marin is widely known with their experience on ship hydrodynamics, and you can see here our facility in Wageningen in Netherlands. In English it's called Wageningen, and it's proper name, as you already know that. And since 32 this marine company continues, and we have got more than 400 employees, and we are serving to following markets like a defense and infrastructure and the yacht and oil and gas markets. And we are using our simulation capabilities and model testing capabilities with prototypes and simulators with virtual reality. And after ships are built, we are monitoring them in reality, actual reality. And you can see some kind of basins we have. I mean, we have got 8 basins, and here in the right upper side, seakeeping maneuvering basin, which is the main one actually, and it has got 170-meter length and 40-meter width and the depth of 5 meters. And I will not give details of those basins, and we have got we don't have enough time for this, but something should be mentioned, that the pressurized wave basin we have in the right bottom side, you can see, and we can reduce the pressure, and we can observe cavitation in more details while ship is being towed in this facility. And those facilities have 3 meters thick walls, I should say. And this is the simulators, but I will pass those to be quick. And what I'm going to tell you today, I mean, I will explain you a little bit more what I'm doing in Marine, because I'm a more structural guy than the hydrodynamic guy, but I found it important to couple the hull structure and hull flexibility to the basin test results. And basin tests, which Yıldız Technical University now has one of them, and it's actually important to couple those two. And I will show you some examples. How are we doing this? I mean, first we are designing the flexible models with the backbones, and we are designing first the rigid models, and after toning them, we are cutting them into pieces. I mean, we call them segments, and those segmented models are being connected by a backbone, which you can see in the bottom there. And it may have different structural properties. And the main aim for this, we are trying to catch, or as close as possible, to get the vertical and horizontal bending vibration modes, which were given by the designer or the shipyard or anyone else, or we can also compute them. And after having those dynamic characteristics as close as possible to reality, we are doing those irregular tests, and we are mainly analyzing the effects of the flexibility on the hull structure itself, on the bending moments, what are the springing effects, what are the whipping effects, and what could be those additional effects of those flexibility. And after designing that flexible models, and we are done actually towing them in the basin, and then the second stage that I'm working on is actually structural response reconstruction from the basin test results. I mean, here, yeah, I should start it. Yes. Can you see? But they are not vibrating, I think. Classical. Yeah. Could you see the video? Or I think you couldn't see.
Bantın üzerine basarsan belki alacak.
you have they all should
119 değil
start in the
sağda.
same.
On the right side, on the band, please. If you press, maybe it will take. It will play. No, on the right side, please press. Just 2 centimeters, right? Yeah, no.
But anyway, okay, not to make it longer, we are measuring those acceleration and vertical bending moments and pressure data from the basin tests. And then we are applying those values in time domain to our virtual model, which here you can see as finite element model. And then we can simulate the same test characteristics, same test inputs in the computer again. And then we can calculate what is happening in the structure itself. So we can decide in detail the structural properties of the ship itself. This is a good combination of the structural capability and the actual basing capability. And for this ship, is it instrumentals? Okay, there are 80 pressure sensors are instrumented there along the ship hull, and then all pressure values during time are being mapped to a finite element model, and then we could create what is happening during the slamming and during the whipping and during the every other things, and then we can analyze in detail what's happening in structural manner in the ship itself by combining those model tests. And these are the places of the pressure sensors along the ship hull. The reds are the pressure sensors and the blues are the wet hull. And then here's just an example of a mapping procedure. We develop our own mapping script for this, and we can map in time domain in time, so we can apply those into a finite element model or every kind of model to get it solved in time manner. And one of the latest tools that I'm actually developing, and I'm the product development manager of this product, this is Markov XMF. And what is Markov XMF? Is a time domain simulation tool for the ship collisions between two ships or ships to another rigid objects. And for this one, we are using the super element method, and super element method is actually not better than finite element, but it's actually stupid finite element methods, finite elements, because they just got a closed form expression, analytical expression of the plastic response of the ship structural components. And then by combining those super elements, we are having the structure itself. I mean, here you can see as a gray structure in the struck ship. And then, therefore, we can do a rapid prediction of a ship collision. And I can give rough numbers so you can get a finite element solution for a ship collision in 2 weeks. And in our Markov XMF, we can solve it in 2 minutes. And yes, you are losing some kind of sensitivity, or it may not be correct enough, but it's good that we can fine-tune our super elements according to experiments that we have in the literature, or we have in our experiments, or we can also fine-tune them according to finite element simulation that's done accordingly, and then we can have a good comparison and good results out of that software. Here is the actual project comparison, and we have compared our simulation data, simulation results with Brave Veritas Sharp software and Elestina simulation, which was done by Aalto University. This was the European Community project, FLAIR project. And as you can see, the penetration values and energies are really close to each other. In the right bottom side, there is an also additional purple line, which was the old software that when I started to Marin, there was an old version. Then I started to develop the new version. And with the new version, we can obtain a better approximation with the finite element solutions. And you can see all those three codes are in a good agreement between them. So thank you very much for watching this presentation. And yes, stop share. Yes, this is the brief introduction. What I am doing in hydrostructural service department of Marine. So I'm not a real hydrodynamicist, so I didn't give you a detailed hydrodynamic presentation of Marine. It's already well known there, but it's good to show how can we combine structural properties or structural dynamic characteristics with the seakeeping basin test results. This is actually important to be able to do a real-time fluid structure interaction.
Thank you very much, Dr. Levent Kaydıhan.
Yes.
Very interesting mechanical and also dynamic problems all together. Of course, they make each other more complicated.
Mm-hmm. And actually talk with our colleagues in Marine that I told them that you, and I mean Yıldız Technical University has now a good looking small basin tank, seakeeping tank. And they said, okay, we can do together a technology transfer project, which I should mention, I think here, and then we can transfer the technology, transfer the know-how, and transfer every kind of details, if you like. That's also another possibility.
Yeah, as you informed me previously, these are very promising plans. Yes, thank you for your contribution. Helping to this cooperation. Thank you very much.
I hope it will be helpful.
It will be helpful, yeah. Now, according to our table, Dr. Emre Uzunoğlu and Engineer Felipe Vittori from Centec, you together, I think, will mention about interesting things. You start, I don't explain.
Okay,
please.
I start and then I'm going to leave the field to Felipe to give you some details. So I'm going to share my screen. Is this okay? Are you seeing the presentation or the presentation mode?
Clear, everything is nice.
Okay, so I work at Centec. Let me give you some very brief information on where I work. Okay. So Centec is a part of the University of Lisbon. Under that, there's Instituto Superior Técnico, which is the engineering institute, and Centec is a part of that. It's not that large. We have about 100 researchers, 40 PhD researchers. We do a lot of projects, more than 50 national projects, 100 European projects. And Shanghai ranks universities in marine and ocean engineering. We are 6th in the world in terms of number of publications and 3rd in Europe. So we do publish a lot of works. So in one of these European projects, it is called ArcWind. It is a very long name, adaptation and implementation of floating wind energy conversion technology for Atlantic region. So ArcWind, I believe, is shorter. It brings together 22 partners from both the industry and the academia. And what we are doing there is 3 platform designs for a 10 megawatt turbine. And it has received European funding of about 4 million euros. So it's a bit of a larger project. Centec's role here is that it is the leading partner and the coordinator is Professor Carlos Queresores. So I mentioned that there are 3 platforms. One is designed by SciTech. It is a bit of a barge. And then the other one is designed by Esteco. It is a spar, but it's an interesting spar that has its tower telescopic. So you can actually lower it to lower the center of gravity. So you can easily transport it. And the third one is the one that I have designed, the Centec TLP. This is what I would call a hybrid structure, a bit of a barge and a bit of a TLP. Normally, tension leg platforms aren't stable. This one is stable. You can tow it into location, and once you install it, it acts as a tension leg platform. So to test this structure, we needed to collaborate. So I mentioned that Centec, I designed the platform, and I did the planning of the testing. And then Universidad Politécnica de Madrid is has helped us to do the experimental testing by allowing us to use their wave basin and setting up the model and going through this. And we asked for help from CENER to do the aerodynamic testing with us. When it comes to aerodynamic testing of these structures, crude scaling, you are all familiar with it. You've been testing ships this way, that is fine for waves. But when it comes to aerodynamics, the turbine testing is a bit complicated because it's very Reynolds number reliant, so it requires a novel solution. CENER's method of involving this, to addressing this problem, is to use a drone that replicates the thrust forces and the moments from the turbine. So with Felipe together, University of Madrid, CENER, and CENTEC all together, we recently published this work, hybrid scale testing of the TLP. And Felipe is going to tell you how exactly have we gone through the testing phase and how we have addressed these problems in terms of aerodynamics. So this is all I want to say. So I will leave the field to Felipe, who has joined us.
Thank you very much, Dr. Usunoğlu.
Let me stop the sharing. Okay.
Yeah.
Are you able to hear Felipe? Yes. Felipe, I can't hear you. Maybe if everyone.
Felipe.
Yes, we can hear you. We can hear you.
Okay, then it's me. Okay, no problem.
Excuse me, I should say that Professor Atlar, Professor Demirel, and Savşay Day colleagues, there are enough time to for their presentation. I take care the time, allow time.
Okay.
Thank you.
Okay.
We cannot hear Felipe.
I can't hear either.
Not yet, Felipe.
Not yet, Felipe. Mm-hmm.
Can it be on Zoom settings, maybe? That
May I suggest we continue with other colleagues, then we come back to Felipe Vittoria, I think. Can we return back to you after about 20 minutes? I think Professor Atlar, you start with your presentation to save, to use time. Thank you very much.
Okay.
Sorry, Felipe, we go on.
Thank you, Ahmet. Thank you, colleagues. I just share my screen, first of all. Hopefully successful, I can share it. And coming up. Can you see my screen, colleagues? And also, can you hear me? Excellent, thank you very much. So let me also get my pen. Okay, that's my laser pointer. Okay, right. as Ahmet kindly suggested, I am Mehmet Atlar from University of Strathclyde and Department of Naval Architecture, Ocean and Marine Engineering. I can see my two colleagues also, Yiğit Demirel and also Sasha Dai is there. So this is very good. So I'd like to talk a little bit about some specialized hydrodynamic testing facilities that could be interesting for you. Otherwise, it would be a very boring presentation. So, like Levent did it for Marine. By the way, I know Marine very well, Levent, and I hope to meet you when I next time visit Marine.
Sure.
And anyway, so in our department in Strathclyde, we have various capabilities. Very briefly, we have a large towing tank, which David is handsomely giving his picture in front of it. I'm sure he will talk about. We recently have a very small ocean tank built. You can see that accessible by the laser-based devices like PIV and LDA and etc. So this is a very new one. And of course, we have a full mission bridge simulator. This is also very recent. A little marine engineering lab, and we have a 33-foot or 10-meter plus yacht that our students enjoy actually sailing. So we can go on board of a ship and we can measure underwater radiated noise, observe cavitation, propeller cavitation in full scale by using borescope techniques and etc., motion measure, etc. So these are all standard kind of capability and hydrodynamic facilities we do. But today I'm going to refer to three different unusual equipment. One is fully turbulent flow channel, which I will go into the detail, which we have this one about 2 years ago, manufactured, built and established. Then I am going to explain. And the second thing is a dynamic biofilm farm, like to generate the slime or the fouling, and then you experience at sea when you submerge any piece of sheet or metal or ship or propeller, they all get biofilmed or biofouled. But we want to do this very quickly. And so to have a look at its effect on the coating and etc. So therefore, we put together a dynamic biofilm farm to generate the biofilm in 1 week, 2 week time and etc. And then the third equipment that I'm going to talk, this is a project, by the way, it's not in yet, but it will be interesting to tell you. I call this one multi-purpose, multi-phase flow channel. I'm just going to go into the detail. Let me just start with the fully turbulent flow channel. What is a fully turbulent flow channel? Colleagues, this is actually a very, very narrow channel. I'm talking about maximum 2 centimeter or maybe 1 and 1.5 centimeter narrow channel. You can actually push the water with a very high velocity and then build fully developed turbulence boundary layer, very similar to the ship surface, how the ship surface actually, when you apply the coating and etc., build up the boundary layer. So then you can measure actually the hydrodynamic characteristics, the boundary layer characteristics, the pressure and etc., then extrapolate that to full scale. So that's all about it, to generate the surface flow as realistic as possible, because you can't do that in a towing tank, you can't do that in a cavitation tunnel and etc., because your Reynolds numbers are very low and so on. So therefore, you really need to narrow the channel. So that's all fully turbulent flow channel. If you may ask me how many there are fully turbulent flow channel around the world, I would say maybe not more than 10, I would say. Maybe recently there were very few. And one of them we developed when I was in Newcastle University, and the other one when I came to Strathclyde University, this one, the one that you are seeing it here in Strathclyde University. So the sizes is here, like something about maybe 7 meters one side to the other one. And there is a tank here. This tank full of seawater, obviously fresh water you can use as well. But the seawater, why is seawater? Because we would like to see surfaces covered by biofilm, like slime and maybe a very juvenile, newly developing biofilms like barnacles and etc. And then we wanted to understand how they affect the surface drag, especially when there is a coating. As you know, we put coating on the surfaces to fight against the to fouling and etc. So therefore, you can circulate seawater. You can see there is a very narrow channel here. And then in this narrow channel, there is a special section here, measuring section. There, actually, we can put different surfaces and then to see so-called a kind of different flow characteristics and so on. And you can also see that we can combine this facility by using particle image velocimetry, laser Doppler velocimetry, and etc. So maybe I go more into detail now. Okay, there it is. The water actually here is being pumped by using a pump here with a high velocity and coming to this kind of a narrowing section, and then it's being accelerated, and then you can see that then from this section to here, channel narrowed, and about, in this case, in our case here, almost 2 centimeter width, and then flow becomes fully turbulent, and then this section, we call it measuring section, we put actually surfaces. You can see that there is some sort of a plexiglass surface here. Of course, that this surface can be painted, and also you can have a painted surface. We put top and the bottom. And then obviously when the flow passing through, you can see that there are holes in here. These are some sort of taps, and then you can measure the pressure difference, one hole to the other one. Either you can use these two very close one, or one at the top, one at the leading edge, one at the trailing edge, and then over the entire surface. By using this pressure drop, then you can work out actually the frictional drag. So this is a very, very simple, practical, if you like, a kind of a mechanism to measure, if you like, the frictional drag characteristic of any kind of surfaces. You can see that one of our colleagues is putting a surface here. If you ask me, what is the size of this panel? This is about 60 centimeter and then 25 centimeter a panel in here. So if I move on to the next, so of course that these panels can be nothing on it. That is a smooth surface. We call this one reference surface, but you can apply a kind of a different surface coating on it. This is actually a foul release coating, like a silicon based, a new generation coating. And also you can develop on these surfaces some sort of a biofilm, and then slime and etc. You can see that in the sea, this surface has been grown with coating. Once you have these surfaces, then you can also measure by using profilometry, laser-based profilometry, roughness characteristic. So then after that, you can put into this so-called measuring section, push the water. By the way, the speed, we can go up to 15 meters per second. You're talking about 30 knot speed, you know. That means the shear forces or the shear stresses on the surfaces can be as high as in the full scale. So you have, because you have a fully turbulent flow there, so then the characteristic very close to the surface should be similar to the surface locally at the ship. So that's all the crunch actually is about. So once you have this so-called the characteristic pressure drop, as you can see the simple formula here, pressure gradient can be related to shear stress. Of course, shear stress can be related to the frictional drag. That is your frictional drag. This is your Reynolds number. This is your frictional drag coefficient. Once you have this one, you can actually relate this to roughness characteristics, roughness-based Reynolds number, and then you can determine your wall function. That wall function can go into the computational fluid dynamics, and then there you can represent your surfaces, and then you can actually simulate full-scale ship resistance. That's all about it. This equipment here actually is a complementary equipment, taking the so-called complicated surface hydrodynamics to simulate in your computational fluid dynamics and make a realistic prediction in the full scale. You can see that in here that there is actually the frictional drag measurements based on the pressure top between 1 and 6. That means at the leading edge and trailing edge. 2 and 5 a bit narrower, and 3 to 4 next to each other, you can see that they seem to be giving quite a good sort of correlation with the theoretical curves by Dean in here. These are, by the way, measured on completely smooth surfaces. When you measure frictional drag on, let's say, foul release coating or another type of coating, let's say self-polishing copolymer, you can see that these curves are going here and there, so then you can get all this information. This is all about it. And these are quite unusual equipment that we use. And my colleague, Dr. Demirel, he is an expert in the computational fluid dynamics. So then he can take these and then also make a simulation and experimental data, put it into the computational fluid dynamics and then building wall functions. So then he can make quite realistic simulation of the vessel with the typical coating, different type of coating in full scale, and even covered with some sort of fouling. Let be slime, let be barnacles, or let be other type of fouling. Okay, so I mentioned to you that this surface can be covered by slime. How we generate the slime? Really, there are ways. When I was in Newcastle, and we actually designed and built this research vessel, Princess Royal. With this Princess Royal, I also there is a moon pool there. In this moon pool, I developed a special strut mechanism. In this strut mechanism, I attach 1, 2, 3, 4 in each side, 4 in the other side, 8 different test panel. These test panel move with the ship and then develop biofilms on them, fouling. Then after that, I took that, put it into my fully turbulent flow channel and measure what is the impact on drag. But this takes time. You're talking about 2 months, 3 months, 4 months. You cannot afford that when you're doing a quick research. By that time, you need a dynamic so-called slime farm, dynamic biofilm generating mechanism. You can have that like a jet type of unit. You can see that there is actually a box here, and then in that box, in the left and right, or the port and starboard side, you can put your test panel, and then by pushing the seawater on it, and also seeding, and then putting the seeds of the biofilm from the sea, you can develop immediately, let's say in 2 weeks' time, biofilm. So then you can have the similar 3-month-old biofilm here from maybe in 2 weeks or 3 weeks' time. That's called dynamic biofilm. We had this one in Newcastle University. When I come to Strathclyde, we never had such a facility, but we thought that we could be smarter. Maybe we can build some sort of a drum like that, like a rotor, rather than a jet, because jet type dynamic biofouling farm may have some deficiencies, having a smoothly harmonized fouling on it. So we thought that maybe having a rotor and then spinning this rotor can be more economical and more stable. So therefore, we designed this dynamic biofilm farm. And also, of course, we did some CFD and have a look at that, how the biofilm, how the flow developing on it, and etc. After certain design iteration, eventually we said that, okay, then we're going to put this rotor in a vertical sense. So we have the rotor now in rotating in vertical sense. As you can see, this is hexagonal, so 8 surfaces. If you 8 multiply by the 2, there are 16 surfaces. Then you can put 16 different coating, and then in 3 weeks' time, you can develop all kinds of different slime on them, and take this one and test in your fully turbulent flow channel, and eventually predict the flow characteristics and fouling characteristics, and then the coating characteristics. This actually is being manufactured, funnily enough, in Turkey, in Izmir, is about to be posted to transported to Newcastle, and then we will be putting in our laboratory. You can see how this the tank is being done and rotor is being built, and by the end of the year, this will be providing us the foul surfaces. Hopefully, we will test them in our fully turbulent flow channel. So this is second interesting facility that I would like to mention to you. And then finally, actually about a month ago, together with my colleagues like Yeet and other colleagues in the department, we decided to have a new facility which we call multi-purpose, multi-phase flow tunnel. What is this? You may see here a kind of medium-sized cavitation tunnel. This is an old cavitation tunnel, but we are actually modifying, enhancing this cavitation tunnel as such. This tunnel will be able to circulate seawater. It has got a very high quality stainless steel shell, and then we will be able to put a seawater in it. When we put the seawater, and then we will be upgrading the measuring section here, that will be much more accessible. Almost everywhere is rectangular channel. There we can use our laser-based equipment as LDA or PIV and also DIC, etc. Any kind of sophisticated flow measurement system that we can do. So what is the good thing about this one? Now, if we have a facility like that, we can test any surfaces, including propellers, foils, and the surfaces with air lubrication under the real sea surface condition. When you put the seawater, then you can take the effect of salt, you can take the effect of air bubbles, and then you can take the effect of surfactants, and then solid materials and everything. That means water quality exactly or near reality is being taken into account. This is very important for cavitation, very important for cavitation inception, very important for air lubrication. So we have submitted almost 2.3 million pounds of project proposal to our Engineering Physics Research Council under a 3-year program. And then, as you can see here, in year 1, we will be all getting all the facility somehow is being designed and manufactured. In the year 2, we will be installing into our Kelvin Hydrodynamic laboratory. And then in year 3, we will be conducting certain demonstration projects involving hydrodynamic drag, cavitation, and also underwater radiated noise, and then all the other stuff. So you can see that this tunnel is unique. I would say the only tunnel will be in the world circulating seawater at such size. And also you'll be conducting research on air lubrication, underwater radiated noise, as well as the coating research, and then so-called propulsion research and etc. So personally, I'm very, very excited about. Then by the end of the year, we will be getting the results, hopefully that we can be able to get this 2.3 million pound support from the United Kingdom Research Initiative funding, and then we can get this one in 2 to 3 years' time in our department. That's all, colleagues, and thank you very much for listening me. And there's nothing much more scientific that I can show you in numbers and etc. But if anybody is interested, you're more than welcome to contact us, and then I will be more than happy to demonstrate this. That is end of my presentation, and thank you.
Well, thank you very much, Mr. Atlar. So we are working on similar projects and objects and studies. So I will certainly get in contact with you. I mean, I will let you know, I mean, our interesting colleagues about this presentation. And I think it will be good to work in a I mean, European Committee project or something together on the similar subject. Thank you
absolutely, absolutely, Levent. It's very nice to meet you, actually. And I know that Tom van Tervischa.
Yeah,
Tom is a very great colleague, and then we do a lot of collaboration with him, and I will be very much delighted and to collaborate.
Yes, sure.
Thank you very much, Professor Atlar. Of course, biofoiling, the environmental effects on the hull surface, propeller, other water chests, so on, are important for energy efficiency, operational kind of efficiency, so on. But research is needed to understand all these natural phenomena there. Your experimental facility design is very, very, very appreciated. We will listen again, I think, all your presentations. We have strictly 25. We have strictly 25 minutes for Felipe Vittori if Serdar Beji, Professor Serdar Beji comes. He will be late because of the doctoral exam. Please, Felipe Vittori, are you ready for the?
Yes.
Oh, very good.
Ah,
please.
Great.
Please.
I was very worried.
Okay.
All right. I'm going to share my screen again.
Interrupt. Sasha Dai, do you have something to show? Should I share time for Dr. Sasha Dai or not?
Well, I can make my presentation in 15 minutes. Is that okay?
We have now 24 minutes. Strictly 24 minutes. After that, other sessions will start. So 12 minutes.
Okay, I'm gonna.
Sorry, 12 minutes and 12 minutes for both colleagues. Thank you.
Okay, I'm gonna do this fast. Thank you again for the invitation to do this presentation. I'm going to talk about the software in the loop, the seal hybrid method for scale test of floating wind turbines. I'm going to give an introduction about floating wind, the software in the loop method, some campaign result, and the current development of the seal, and brief conclusion. As Emre already said and show, floating wind technology has been accelerating its commercial deployment in the last few years. One example is the high wind floating wind farm at Scotland. For the design of floating wind turbine, we need numeric tools, and these are limited and require scale tank test data. As Emre mentioned, there is a scaling conflict between the Reynolds numbers and the Freud number that make very difficult to having complete similarity. So, however, it's possible to still obtain a valid dynamic from the platform and the wind turbine during tank test, as long the forces are preserved. One example of this is the tank test campaign during the OC5 project, as you can see here, the semi-submersible and the rotor. These alternatives are based on wind generator that then you can use a drag disc like the one used by Rodier and their collaborator on the wind float, or a low Reynolds rotor here during the INWIN project on the triple spar. There are challenges with this wind generator method, like the dimension of the wind generator, control the quality of the airflow, the difficult to match the prescribed turbulence, and also the weight of the rotor nacelle assembly. At the end, this is cost and time. Here at CENER, in order to reduce this challenge, we developed this method called software in the loop, or SEAL. And this method is based on replacing the rotor by a force actuator like the ducted fan that is going to be fed in real time by computation of the aerodynamic loading. So with this method, we want to take advantage of the aerodynamic calculation that are quite well accepted, and also about the experimental hydrodynamic that is our reference tool. So I'm going to show how the seal works. Here we have a tank test facility with a scale floater, and we capture its motion through our system. Then we scale up this motion, and we calculate the total aerodynamic thrust done by the wind turbine, considering this motion. So then we scale down this force, and through the ducted fan controller, we feed the force actuator and produce the required thrust. All this is done in real time. So as you can see here, this force is the motion. I mean, the wind turbine is coupled. Wind turbine response is coupled with the motion of the floater, as it is in the in the full scale. So with the SEAL method, we are considering turbulent winds, time variant wind, the wind turbine control strategy. We are considering the aerodynamic damping. We can produce, replicate scenarios with wind and wave misalignment, and also some failure of blade pitching. In this method, of course, we have simplification, like the aerodynamic loads are applied at the rotor center. The rotor flexibility is not considered. The generator torque is neither considered, neither the rotor moments. The main limitation of this method is the extreme shear event. We cannot replicate on tank testing, the change in wind direction, and also some other event with failure of the blade pitching. During the application of the method, there are challenges. We have to keep the synchronization between the acquisition frequency and the simulation time step. The communication with the motion tracking we have some situation of overheating of the fan, and we need to, during the calibration phases, of course, before the test, check the frequency response of the fan that we use. We have been developing this method since 2012 here with the floater, in this floater with Acciona. Then also we made some campaigns during the InWind project with this OC4 semi-submersible, also with the Triple Spar. We participate in campaigns at Cork here with the Delta Wind floater. Also for TLP, this TLP designed from Iberdrola. And we also came from testing 5 megawatt wind turbine to 10 megawatt wind turbine, and also 6 megawatt wind turbine like this one from Olaf Olsen. And here also we used some campaign with the Steico advanced floater. One example of the result that we can obtain using this method are the couple response of the platform of the surge of the platform, as we can see here, under turbulent wind and irregular waves. Here you can see how around the natural frequency of the surge of the platform. It's a wind-dominated region. Here is the wave region. In this case, we made validation with some numeric model, as you can see here, the blue and green line. In the green line, we are using a numeric model with just only first order hydrodynamic potential. And you can see the agreement with respect to experiment. Also in the pitch response, we find the same agreement. Again, wind is kind of the loading dominating this response. And here you can see more clearly the wave region. Now, here is this an example in time domain of the platform pitch response. The dark line represents the experiment, and blue and green line are the numerics. Again, we obtain a good agreement. And here, this is the blade pitch angle produced by the control strategy, of course, considering the platform motion and the turbulent winds. And again, this we found this very interesting, this agreement. Now, that was the seal. Now I'm going to show some of the current development. Right now, we want to introduce more, not only thrust, but also the moment. And we are moving from a ducted fan into a multi-propeller system, where we can introduce not only thrust, but also the moment in the Z direction and in the Y direction, as you can see here. And now we can tackle this previous limitation. also, in this way, we can prevent the overheating of the fan because now we are dividing the truss into several motors, so the overheating is less frequent. And these new motors from the drone industry have a very fast response. So we improve the response of the force actuator considerably. Here is our calibration rig at CENER. Here we test our actuator before going into tank. Now we are going to, during the Arwin project that Emre previously presented, we put into test our new actuator. Here is the Syntec TLP. Some of the motion tracker are here. We were working around in this area. And with the new seal, we were able to improve the dynamic of the response. Previously, we just introduced the force, and the result was a kind of a plane motion. I mean, just surge, heave, and pitch. Now, with the moment, we can have also a yaw and sway response. Here in this plot, you can see the red and dark line are the old seal, and there is a practically no response at the yaw degree of freedom of the platform. But when we use the new seal actuator, the blue and green line, now we have a response, a response done by the aerodynamic loading. This is the other platform from the Arwin project. This is the SAF 10 megawatt barge. In this test, the scale factor was 49. This platform was meant to use a single point mooring system, but at the time of the test, it was not ready. So it has a common retention system for ships. And we just consider a wind and wave collinear. Again, here is the actuator. And in this case, we did a validation of the experiment, that is the blue line, with numeric model, with numeric result obtained from OpenFast. And we found a very interesting agreement, as you can see here. Of course, the peaks are not reached, but still, this is an important result. Here is the PSD for your response, and this is we consider this a good agreement.
Thank you very much, Felipe Vittori. I don't want to interrupt. I think you show the conclusions page, then we can pass to Sasha Dai. Thank you.
All right.
Thank you. In 1 minute. You tell your conclusions, so I don't want to interrupt your conclusions page.
Okay. Okay. I'm going then to finish this. Yeah. Well, as we show, the seal method is an efficient method to capture the wind turbine influence on the floater dynamic. It can reproduce the system damping, the low frequency dynamics, prescribe wind turbulence files, and the wind turbine control strategy. That is very important. It is a low cost and time saving methodology. The rotor loads are based on computation, and the drone technology improved the actuator performance, including the rotor moment and increasing the response speed. And now, thank you very much for your attention. I'm sorry for the technical difficulty. Any question, you can forward me to any email. Thank you.
Thank you. Thank you very, very much, Mr. Felipe Vittori. The time is limited for Sasha Dai. Please, you have exactly 10 minutes.
Okay, I'll try to finish everything within.
In the 10th minute, I will warn you, maybe the system will cut. I asked my friends to extend the time period. I hope. Please, we are listening to you.
Okay, can you see my screen?
It is clear, yeah. please.
Right.
Go on. Yeah.
Okay, so good day, everybody. So first of all, I would like to introduce myself. My name is Shai Dai, and also known as David Dai. I am the project manager of our carbon hydrodynamic laboratory. And today I'm going to talk about, briefly introduce the carbon hydrodynamic laboratory facilities and briefly introduce some recent research activities. So our carbon hydrodynamic laboratory located in Glasgow, Scotland, and it was established back in 1960s by the University of Glasgow. The facility was then handed over to Strathclyde when the two universities merged the naval architecture and ocean engineering department. It was the largest towing tank in any UK universities for many years until University of Southampton built a larger one. So the external of the lab looks exactly the same as it was first built, but during the past a couple of years, we have undergo some major upgrade of the facilities, which I will talk about. So we have a workshop equipped with both modern CNC machines and conventional machinings. So with the help of our experienced technicians, we can build 90% of the model by ourselves. So for ship-like structures, we use the composite mold methods as shown in this picture. Can you see my laser point? Right. So during the past years, we have accumulated quite a few ship molds like Korean container ship, DT5415, etc. Besides, we now start to use 3D printing technologies for some complex model parts. Next, here is some examples of the models we made in our workshop. For example, we made offshore decommissioning vessels, DT5415 combat ship, catamaran crew transfer vessels, and semi-submersible type floating wind turbine. Also, here is a model that represents marine growth, which is made by 3D printers. So our main facility is just above the workshop. It has a length of 76 meters and a width of 4.6 meters. The water depth is changeable and can be filled up to 2.3 meters. The maximum speed we can achieve with our carriage is about 5 meters per second. So in 2010, we have upgraded our wave makers to a flat type force-controlled wave maker. The maximum wave height we can achieve is about 0.7 meter for regular wave, with a frequency range from 0.2 to 2 hertz. At the end of the tank, we have a 14 meters long wave beach, sloping type wave beach, topped with porous media. This optimized wave beach can provide typically 5% reflection coefficient across all the wave frequencies that we are interested. So in addition to the large towing tank, we recently acquired this 3D compact wave tank, as briefly mentioned by Professor Mehmet in his presentation. So this wave tank has 8 pedal wave makers and is able to generate directional spread wave up to 40 degrees. Of course, Professor Mehmet has talked about the flow FDFC in detail, so I will just skip this. Okay, so above is all the facilities we have at the Carbon Hydrodynamic Laboratory, and we are looking forward to expand our test capability by bringing in more test equipment. For example, those mentioned in Professor Mehmet's presentation. Next, I'm going to quickly talk about some experiments we have done in the past 5 years. So as a towing tank, apart from conventional resistance and sea keeping test, we have done quite a few resistance and sea-keeping tests within restricted waterways. So for example, one of our graduated PhD student investigated the Korean container ship advancing through canal in 2018. And the model canal showed in this picture is a scaled model of the Suez Canal. Another interesting experiment we did in recent years is an experiment examining the surface roughness of on the ship. So we tested a KCS, which is covered with sand, and the result was compared with the smooth hull experiment. This project was led by my colleague, Dr. It. Well, alongside some commercial ships, we did some interesting water sports related experiment as well. For example, sailing dinghies. So water sports sailing boats are normally much smaller than those conventional ships, which provided us with the chance to test the full-scale sailing dinghy in our tank. So in this picture, you can see the full-scale sailing dinghy. And back in 2019, we tested a 1 to 2.5 scale model of this model. And once we finished the test in the tank, we tested the exact full-scale model in open water as well. Results of the total resistance are demonstrated in this figure. The agreement between the tank test and the open water towing test is inspiring despite considerable different test environment conditions. So recently, one of our PhD students is looking into ventilation on a T-shaped hydrofoil, and she used high-speed camera to capture this phenomenon. Okay, so in addition to ship-related tests, our tank is actively involved in testing marine renewable technologies in recent years, including offshore floating wind, wave energy, tidal energy, and hybrid solar platforms. We have recently completed a floating wind turbine, floating wind round-robin test funded by EU H220 program. The program involves testing the same semi-submersible model in 4 different facilities to examine the factors leading to discrepancies in the test results between different facilities. Overall, the agreement between each facility are excellent in the wave frequency range. Now, Philippe has just briefly mentioned about the TLP test designed by Ibrugila. We, Kelvin Hydrodynamic Laboratory, executed that experiment using Synergy developed software in the loop technology. More recently, we have developed an AI-based wind load simulator by ourselves. Despite of the merits of the software in the loop method, it has several limitations. For example, it requires modification of softwares, so the software can take real-time platform response into consideration. And the accuracy of this software in the loop method can achieve is at best at the software level. So our AI-based wind load simulator takes the wind condition and the response from the platform as a training set of data. And then we use AI-based algorithm to train the model so that the model can correctly represent the hydro and aerodynamics interaction. Because it is response-based model, that means we can actually take field measurement as a training data and train our model to correctly represent the coupling between the aerodynamics and the hydrodynamics. As illustrated by this figure, we can see the current model can correctly reproduce the simulation data from the OpenFast numerical simulation tool. As for tidal energy, apart from testing of conventional horizontal and vertical axis tidal turbines, our department has also carried out some bio-inspired innovative design. For example, a hump whale fin inspired new design of tidal turbine blades. So with the help of our excellent wave making capability, our tank is closely working with the Wave Energy Scotland, and we have tested more than 20 different types of wave energy in the past. Currently, we have a couple of projects that is with that comes with the idea of flexible structure. So here, I'm showing two examples. On the left side is a wave energy converter called Anaconda, and on the right-hand side is rubber-made buoy that is designed by TTI Marine. So the test of this TTI Marine designed rubber involves both above water and underwater Qualys camera system to investigate the deformation of the buoy and the different pressure loadings. In addition to commercial...
2 minutes, sorry to interrupt. In 2 minutes, you and me conclude this session. Thank you.
Okay, so another very interesting topic is extreme wave loading. We used focus wave groups to simulate extreme wave loads, and we used a technique called four-phase decomposition to separate the higher order components out of the total force. And apart from the above engineering-focused research activities, we are actively looking into new technologies into hydrodynamic tank testing. For example, one of our PhD students is currently using image processing techniques to reconstruct some fluid mechanics and hydrodynamics problem in computer. The above animation illustrated the reconstruction of the wave field caused by a free fall object. We are looking into...
Yeah.
Thank you for your attention.
I am very sorry. I'm afraid they interrupt the system. Automatically interrupts itself. For that reason, I would like to thank to these esteemed distinguished professors and researchers one by one on behalf of Congress GMO Shipmar organization and for all on behalf of our colleagues, all colleagues, I thank you one by one to each participants, full of experimental research. Each one has its own value, high value. Of course, the time is limited for this large time research, for this large time research results. We started with Claudio Pensa. Thank you. I was very happy to see you.
Nice to meet you.
To Fabio De Luca, Emre Uzunoğlu, Sasha Day, David, to Professor Mehmet Atlar, Yiğit Kemal Demirel. Levent left earlier. He told me he had a meeting. Thank you very much before the system interrupts itself.
Thank you, Ahmet. Thank you very much.
Again.
Thank you.